Welcome to Advanced Data Analysis 1 with me, Erik, Erhardt, Professor of Statistics at the University of New Mexico. In this video, I will help get you started with multiple regression and introduction. Alright, so we will begin by downloading the QMD and, that's it, the QMD file to our working folder. And then we'll go over to RStudio, open it up, choose the folder, choose the file, set the working directory, and render. So I'll admit this, in Advanced Data Analysis 1, it's my opinion that multiple regression is a little premature for the class. So we're going to cover it in a gentle way. In fact, I've got all of the code for you, and the main job for you is to interpret the different aspects of the problem. So I like this problem a lot. It comes from the Northampton Rail Trail System. I used to live in Western Mass and miss it very much. And this is an old railroad track that was removed and a bike trail was put in, and it's a lovely place for biking. And this data is available in the Mosaic data package. So you might just run this command once and make sure that you have the package on your computer. The other stuff is typical stuff that we install there. Just so you can see where this is at. This link here will bring you to the map of the trail, and this green line here is where the trail is. And if we zoom in on it, this Chestnut Street is where they were taking measurements for this data. If we drop in here on the trail, you'll see what a nice bike ride this is. Okay. Anyway, there's a little bit of a diversion. Anyway, so what we're interested in is the volume, that is the number of people who are using the trail on any given day, depending on what the high temperature is for that day and what the cloud cover is that day. Okay? Maybe people like going out in the sun. Maybe people like walking in the, when it's cloudy. Do people like it more when it's hot or when it's cold? We're going to learn those things with this multiple regression model. So let's see. I think I will, let me just walk through the stuff in the HTML because it's much nicer to read than the RStudio. So we start by reading the data set in from that package. We convert it to a tibble. It works just fine as its default data frame data class. And we're going to select just the 3 columns that we need. There are about a dozen columns in this data set. And then later on, if you decide that you need to transform a variable, you could do this transformation in this mutate statement. Right now, everything in the mutate statement is commented with the pound sign, so nothing gets changed. And so then the structure of the data set has 90 observations, 3 columns, and these are the column names. They're all numeric data types. Okay. Here's some summaries. And the summary is really just to give you a sense of what the minimum and maximum values are, so the range of the data, but also a sense of whether we have skewness right away. Right now we've got mean and median almost equal. That says to me that we're probably looking at a symmetric distribution for volume, which in my opinion immediately is sort of unusual, because any number that often is bounded below by 0 and is positive is often right skewed, where there's lots of observations that are small and a few that are very high. So we'll see soon when we plot the data whether what's going on. But based on this plot, or based on this summary, it looks like a symmetric distribution. The high temperatures, 41 to 97 Fahrenheit, with mean and median pretty close, again somewhat symmetric. Cloud cover is measured in this unusual unit octas. These are eighths, effectively, but the eighths are renormalized to tenths. So that's fun. At least when you're a pilot, you often talk about, clear, few, what is it? Few, scattered, broken, overcast as sort of sets of eighths of cloud cover. Okay, so this is bounded from 0 to 10. It's New England, so there are going to be a few days where you don't have any clouds, but most of the time you're going to have clouds, and often you'll have some completely overcast. All right, so the scatter plot matrix is a way of visualizing all the data at once in paired relationships. So this may be the first time we're seeing this plot. I have modified this GG pairs, or set the options for the GG pairs plot. GG is, right, grammar of graphics. Pairs is because we're looking at pairs of variables, all pairs of the variables. And this, I'm just changing some options, primarily because the default puts the first variable, or puts the scatter plots on the lower diagonal, or the lower triangular part of the matrix. And I prefer to put the first variable as the response variable, and then put the scatter plots in the top right, so that the first variable, the response variable, is on the y-axis, and the other variables like high temp is on the x-axis and cloud cover is on the x-axis in this comparison with volume. So this is how I prefer to see it. I also put some lines on there. So let's see, the upper corner, if you've got continuous variables, we add a smoothing line without the standard error line, or standard error bars around the regression line. For the lower diagonal, we just put the correlation values. Okay, and there are other options for whether you have discrete or a combination of numeric and discrete. And because all of our data is numeric, we're only seeing the continuous options here. All right, and on the diagonal, we've got smoothed density histograms. So that's what we see here. So actually somewhat symmetric for volume, nice and symmetric for temperature, and actually a little bit less skewed for cloud cover. So most of the days have mostly clouds. That's New England. And then very few days, few to zero clouds. All right, so that's a sense of the data. The main features to look at here are the relationships. So volume and high temperature seem to have a positive relationship. Volume and cloud cover have a negative relationship. So more people using the trail when it's sunny than when it's completely overcast. But temperature and cloudiness doesn't seem to have a relationship here. So that's actually very good for regression models. We will investigate this later, what happens when you have correlated measurements for your predictor variables, your X variables. All right, the correlation, and then the bottom left we've got correlation values. So volume versus high temperature, this positive relationship here has a positive correlation of 0.58. This negative relationship here is negative 0.37, and this neutral relationship between the X variables is negative 0.1, very close to 0. And this that correlation matrix can be seen numerically using this rcore function. And we have a matrix of the correlation values. You see that these numbers match what was in the plot. And then down here are p-values for testing whether each correlation is equal to 0. So is 0.58, the null hypothesis is that that correlation is equal to 0. The p-value is very small. We would reject the null in favor of the alternative, which is that the correlation is not equal to 0. Similarly, this relationship shows the relationship, the correlation is not equal to 0. But this one, the correlation is close to 0, and the p-value is large. It's greater than 0.05. Therefore, we would say here that we have evidence, or the data are consistent with the null hypothesis. We fail to reject the null hypothesis and conclude that the correlation here is basically equal to 0. So, all right, now we're going to get into, I do ask you to answer that question there. Anything else before that? Oh yeah, I want you to talk about the scatter plot matrix. There's your answer there. Okay. Okay. I'll try to highlight each of those. So we've got 2 points here. We're going to fit the model and assess the model fit. So here is the linear model function where we fit volume as the y response variable with these two, high temp and cloud cover, as the x variables. And that linear model fit goes into LM fit, and we can do lots of things with LM fit. In particular, we can pass it to one of my functions to look at the diagnostics, and I'm just asking for the simple set of diagnostics. I've got 8 plots here, and I ask you to provide a summary. First, an overall summary of whether you think the model assumptions are met. Probably you want to write that sentence at the end, and then go into detail about what information you get from each plot. Okay, so you sort of want to work backwards here. Answer each of these and then go back to the top and give a summary. Okay. I'll say overall that these look okay, and that the deviations that we see we probably can't fix with transformations. So in this residual plot, we've got, so the assumptions, I probably should have put the assumptions here. Do I have them? No. The model assumptions are always only on the residuals, okay? And the assumption is that the residuals are normally distributed with equal variance. That means every residual has the same variance as the others. They're basically drawn from a normal distribution with the same variance. And they need to be independent, which we assume is true just based on the way the data are collected, or we know it to be true based on how the data are collected. Yeah, that's it. So here we've got a histogram of the residuals. We have a black smoothed density curve, and we've got a red normal curve. And so our job is to ask, do these look normal? So does the black curve look like the red curve? We have 90 observations, and those are pretty different. This distribution is very peaky. A peaked distribution is called leptokurtotic, and whereas a flat distribution is called platykurtotic. And a leptokurtotic distribution, it can be problematic for us because we have outliers to each of the tails. So the middle sort of looks like it might be roughly normal if there was less variability, but then there's more observations that go out to each tail, and those extreme observations in the tail, as you know about influential observations or outliers, they have the potential to influence the mean and also the variance or the standard deviation. So the more points you have far away from the center, that may be inflating the variance a bit. In this case, because we've got points that are on the low tail and the high tail together, they sort of balance a bit, and the mean is going to be, the mean for the residuals is always exactly 0. But the point is that the center, like this peak, is actually right at 0. So we don't have, it doesn't seem like it's going to be influencing the mean very much in terms of having skewness, but we may be inflating some of the variance. That will work against us, right? So the more variance you have, if you think about having signal to noise, or variance is the noise, if you have big noise, then it may be hard to detect whether the signal is there. Okay, that ratio is the t-statistic that we calculate. So this will work against us in terms of significance testing, in determining whether certain features, the x variables, are important for explaining the response variable. So we just have to watch for that. Okay, but I think this is not going to be a killer for us in terms of assessing or analyzing this data set. This QQ plot, right, we have normal quantiles. So if the residuals were normal, here's the residuals on the y-axis and normal quantiles on the x-axis. If the data were normal, it would follow this blue diagonal line, and all the points would stay within those blue bands. Our data are more extreme on the left tail. They're lower than the line, and they're more extreme in the right tail. They're above the line, and that's what we see over here as well, right? We've got these extreme tails that go far out. So yes, this is also telling us that we have leptokurtotic data. The Box-Cox transformation is only helpful if we've decided that the data are not normal. So in this case, I would say the data are not normal. What transformation can we perform that will bring us closest to normality? And this center line is pointing roughly to 1/2. This orange dash line is 1. So this is going to be an exponent that you raise the response variable to. So y to the 1, y to the first power is y. So there's no change when the transformation is equal to 1. This is the center of this, the peak of this curve is pointing to a positive 1/2. So that would be a square root of y. So if we went back up here and did mutated our volume to be the square root of volume, then we could see if that improves our situation with response with respect to the normality assumption. And that is often only helpful when you have skewness. If you have right skewness, a square root distribution, a square root transformation will help with right skewness. In this case, we have symmetry. That is not going to be improved by a transformation. At least not a typical transformation that we would use. So it's hard to fix this issue. You just sort of have to live with it, or use a non-parametric method like a bootstrapped multiple regression, which is also easy to do, but you often need to program that yourself. Okay, so overall we don't have normality, but we have symmetry, and we are aware of the issue that will happen because of that. We will have inflated variance for our estimates. Okay, so far I think this is not this is a violation of assumptions, but it's not going to ruin our ability to use the method right now. If this was right skewed, I would say absolutely you can't use this finite transformation. But symmetry is not so bad. Okay. Here's Cook's distance. This tells you if you exclude a certain observation, how much do the predicted values change? Another way of saying that is how much does the regression surface change? And all of these points are sort of, there's always some tiny points, but the ones that are poking up, there's a whole bunch of them, and they're not all, none of them are very extreme. For me, this looks just fine. Okay, this blue line is just there for reference. There's always a few points that are bigger than it. It's really what I'm looking for is one that's like way bigger than the rest, or two that are way bigger than the rest. This is pretty good. These three are all about the same, and they're less than twice as high as these other 6 or so. So this looks just fine. No point here is having really undue influence on the regression fit. If you remove one of these observations, the regression line doesn't change very much. So great. In fact, it's not a regression line, it's a regression surface, right? We have 3 variables. We have a y variable, and we've got 2 others. We have a regression surface. We'll take a look at the regression surface near the end. This is the Cook's distance versus leverage. We have the influence, Cook's distance on the y-axis. We have leverage on the x-axis. The leverage is the potential for making big changes. It's basically how much of an outlier are you on the x-axis. Think of like a teeter-totter. If you're sitting near the fulcrum, and you push as hard as you can on the top of that fulcrum, the balance point of the teeter-totter or seesaw, you're not going to change the tipping of the seesaw at all. If you push down close to the fulcrum, it's going to take a ton of force to move it. But if you're way out on the end, your 2-year-old can sit down there and raise you up high if you're sitting close to the fulcrum. So if you're way out, if you're an outlier in the X direction, you can potentially have a huge influence on the regression line. In this case, this is really just a way to help explain why a point would have a large Cook's distance, a large influence. In this case, we've already concluded that none of them really do. But if one of them was, then we could look over here. So here's like a couple points up here, right? That are these points here, 17, 8, and 4. Yes, those are those 3 right there. And they're not close to 0 for leverage, but they are sort of in the high, the mid area for leverage. So they are not really close to the middle, but they're not the most extreme points either. They're in a bit. So it's partly their leverage that makes them influential, but they're not, like we've said, we've already concluded that they don't have undue influence on the regression model. The point that has the most leverage, this point down here, actually has basically 0 influence on the regression line, because when you remove it, the regression surface is going right past where that point is already. So when you add it back in, it's not changing where the surface is going. So this is a nice situation to be in. We've got the residuals on the y-axis versus the fitted values. So this is the values that are being predicted by the model, how many, the volume of the number of people on this trail. And this looks great. It doesn't have any structure in terms of where the mean is. It's basically horizontal. We do have a little bit of structure in terms of the variance. But this can be a little bit misleading. There's a lot of points in the middle, and there's a few points on the left-hand side. And the way I understand this is, think about the Olympics, and we've got like big countries and little countries. When you have big countries, and you think of like the most extreme best people at a certain sport in that country, if you've got, like the US or China or India, if they had more money to invest in the Olympics, if you got like hundreds of millions of people, and you take the top 10 people, they are going to be amazing. In fact, the top 100 people are going to be amazing from these gigantic countries. Whereas if you've got small countries like Luxembourg or something, where maybe there's only 1 million people, now the top 10 people are going to be great, but they're not going to be world class like the large countries. And so the more observations you have, the more opportunity you have to observe extreme observations. So here in the middle, these typical days where you get about 400 people on the trail, we have lots of observations around there, so we're more likely to see extreme observations. And so we have more variance, more vertical spread in this range of fitted values. When you have very few people on the trail those days, we don't have very many observations there, and we end up not seeing very much variability there. Same thing for those very crowded days. We don't have a lot of variance there either. So this, for me, is very common to see this. It's not like we have equal variance. We don't see a band of random points of equal spread here. But the unequal spread is explained by how many observations we have in the ranges along the x-axis. So I feel quite satisfied with that plot. Somewhat similar here, don't let your eye be distracted too much by these red curves. They're there to be helpful, but they don't let them control your decisions. You will make better decisions than those curves will. But this looks like there might be this sort of, I guess, I would say this is somewhat similar to the residuals versus fitted, so I won't say anything more about that. And then residuals versus cloud cover. Now this is like a beautiful plot in terms of like having roughly equal spread everywhere. So I think overall, my summary here is that model assumptions are not met because the data are not normal, but the deviations from normality are not going to be problematic for us. In fact, they're going to work against us in inflating our variances. So we're going to make weaker conclusions, potentially, about how important our x variables are. Everything else looked pretty good. Okay? All right. So hopefully that discussion has helped you in that area. All right, so let's now move on to the hypothesis tests. So now we're finally going to see what the model looks like. We provide a summary, and maybe this isn't quite what the model looks like. We're going to see that very soon, but these are the estimates. So we have an intercept, we have high temperature, and we have the cloud cover, and these are the coefficients of the regression equation. So for let's make sure we're answering the right questions. We also have multiple r squared, which we're going to interpret in a moment. So those are the main values. Each hypothesis is testing conditional on all their predictors being in the model, whether the addition of the predictor being tested explains significantly more variability in volume than without it. Meaning high temperature, this hypothesis test here, for which we have a p-value, is testing whether high temperature explains variability in volume after having cloud cover already in the model. So cloud cover is already explaining some variability in volume. What additional information does high temperature provide us? And this hypothesis test here is testing whether or not the parameter, the coefficient for high temperature, equals 0 or not. And this is a very small p-value. We would reject the null and conclude that, in fact, this estimate or the parameter for high temperature is different from 0. And this is our best guess for what it is. So let's actually go now into the R Studio, and we'll write this portion because it's going to need some notation. And we can use some R coding to have the number appear for us. All right, so we've already set the working directory. I'm going to scroll down to that section, but probably, as you go, you're going to be running each of these sections. I'm going to click on the down arrow, which runs all the chunks above and down to the top of this one. So we should get some plots. Yeah. I think we're okay. Oh, that's something I just broke. This may be fixed before you get here. Okay, so here LM fit gives us our table. Okay, now there are, okay, so for each regression coefficient, write the hypothesis in notation, report the t statistic and p-value, state the conclusion of the test, and interpret the result. Okay, so we've got 3 tests here, but the intercept's not very interesting. This is the expected. We basically don't have an interesting hypothesis there. That's like, will no one be on the trail if the high temperature is equal to 0 and the cloud cover is 0? So it's a sunny day with 0-degree temperature. I bet people are walking on that trail even in the winter. This is estimating 77 people. So I don't think we care about that particular scenario. So let's just focus on the 2 slope parameters. All right. So for the null hypothesis, I'm going to put some of this in $signs so it's an equation. For H naught colon. So this is a beta value. But let's put a subscript on the beta value. As you know from the H underscore naught, it typesets the 0 as a subscript, right? You sort of see it right here. If we want more than one character in the subscript, we wrap it in curly braces. And because we're going to type a word, I'm going to type the high temp down there. I'm wrapping that in text RM so that we're using a Roman font rather than a slanted font. I like to do that because I only want the slanted mathematical font to appear when we're actually dealing with variables. And if we're using a word to read, I just set the text as upright so that it's, I don't know, it looks different. Okay, so is beta equal to 0? Okay, that's our hypothesis. Let's see. We can sort of make some sublists here. For h not equal to 0, we have the t statistic is, and that t statistic is in this column here. That's the, okay. Do you remember how to calculate the t statistic? It is related to estimate and standard error. It is the signal to noise ratio. So if you divide 5.4 by 0.78, you'll get 6.8. Okay, so we want to pull out that value. Now if we want, right, we've got this LM fit object, and we've got this summary. We just, yeah, let's get rid of that. Okay, we know that this produces all this output here. So if we want to see what all the objects are, we can look at the names of this object, and then we can pull out the thing that we care about. Look at that, there's 11 things, but one of them is coefficients. So the summary fit $ coefficients. Let's take a look at that object. That is our table. Fantastic. So now we just need to choose, based on rows and columns, our t statistic. So for high temperature, this is going to be row number 1, 2, and it's going to be column 1, 2, 3. Okay, so we'll try to get row 2, column 3, and see if that gives us what we want. Row 2, column 3, 6.85. Perfect. So now we've got a way using R to fill in this value. So the t statistic is equal to that, and I don't know. Usually I go three decimal places. I don't know, it doesn't matter. 3 or 4 is okay here. So that's what it is. 3 is probably just fine. So you know what I'm doing? See what I'm doing here? I'm taking the code that's going to be interpreted by R, and I'm actually, oh, look at this. It auto-completed and put an extra single tick in there. But I'm running the code and making sure that I get a value. Okay? That's really important for you to do so that you know that it's going to work when you compile it. These pieces of code that are in line with your text are a little bit harder to debug than a code chunk. So anyway, that's just a way to check on it. All right, so we have for h naught, beta equals 0, we've got the t statistic is equal to 6.8. What else do we have? We need the p-value. Okay. I'll say with an associated p-value of, and I'm just going to copy the same code, right? The only difference here is I've moved over one column. So now I need to do the 4th column. Let's highlight and control enter. We'll submit that piece of code. 9.6. Yep, 9.6. So we have the number we want. All right, so that's our p-value. So now we need we've got our t and p-value. State the conclusion. Because the p-value is less than 0, or is less than 0.05, we reject the null in favor of the alternative. What is the alternative? Probably it'd be good to state it up here. We've got the null and the alternative. I think in this class we're using HA. Sometimes we use H1. And our equation is that it's not equal, n/ne \ne is not equals. It gives you the not equal sign. Okay, so in favor of the alternative, so we will conclude that the relationship or the slope, same sort of idea, between the response variable, volume, and high temp, after adjusting for the other variables, is not equal to 0. Okay, that's a very verbose answer. All right, now having written a nice answer, you know what? We should probably render it, make sure that we got all this right. Try not to do too much typing and coding without rendering it, because if you don't get something right and you start getting errors, it's nice to figure out, isolate what could have went wrong. But okay, it looks like everything was right here. H naught is this. HA, H naught is equal. HA is not equal to 0. T statistic, p-value. It is, putting. I will show you this. So this is putting this into scientific notation. If we wrap this in $signs, it will be interpreted by LaTeX, and this exponent will actually go in the exponent. So let's do that. We have a p-value of, okay, it's good. So I'm going to put the code inside of $signs. That's fine because the R code is going to interpret that and return a value. And then that value is going to be in the $signs and will then can be interpreted as an equation. Just for consistency, I'll do that for the T statistic as well, because you never know if it, might have an exponent in there. Okay, very good. So having written this well for the first variable, just copy and paste, and then be careful on, editing this part. So I'm trying to copy the word cloud cover. Okay, so this is cloud cover. The coefficients, right? Let me just run that part. Control Enter. Okay, I did copy and paste. Now cloud cover needs to be row number 3 instead of 2. So I'm going to change the first index to 3, and then the p-value, the first index, to 3. And we already know that the p-value is small. It's less than 0.05, right? It's 0.0001. So we have the same conclusion, except that we now have cloud cover as instead of high temp. Good. Let's render it. We'll take a look at that exponent for the p-value, and then we'll move on. Okay, we'll go look at it, refresh the page. Look at that. Times 10 to the -10. Here's a p-value of times 10 to the -4. Okay, very nice. Everything else looks great. Learning a little bit of LaTeX for equation editing is, I think, a very valuable skill. I learned LaTeX ages ago, but there is a guide called L Short, the not so short introduction to LaTeX. Okay, I think this is the current version of this, and this was my reference. It's twice as long as it was when I was a grad student. When I was a grad student, this was like 120 to 140 pages. This number of minutes is actually the count for how many pages this document is. But there's fantastic tables in here. Let me just show you a little bit real quick. Here's the table of contents at last. Sorry, this is super small. So there's the structure of documents, but let's just look at the mathematical part. Typesetting. Okay, quotations, tables. Right, math has its own section because this was designed by Donald Knuth. for typesetting mathematics. It has lots of great examples like this, where there's the text that creates the output on the right. And so what I'm looking for are, there's all these nice examples of like how to do square roots and so on. Fractions. Okay. What I'm also looking for, here's a bunch of special symbols in their tables. Finally, sorry, lots of nice examples of how to typeset complicated expressions very simply. Okay. It is a markup language, so that what you see is not what you get, but better than what you get, right? So you can do all sorts of things. I'm looking for a table. Sorry, guys, this is not a great departure in this class or for this video. But there's tons of tables in here, which I'm not finding right away, of just like the mathematical symbols and the Greek characters and all stuff like that. So I apologize that I'm not finding this right away. Slash alpha, 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 alpha. Okay, well, sorry. All different fonts. The different special functions, limits, the tangents, or the trigonometric functions, limits. Okay. Anyway, if you learn how to do some of that stuff, then it will give you a bit of a superpower when you're working in these Quarto documents. Okay, sorry for that diversion. All right, let's interpret our model coefficients. So if we pass the LM fit and the data set into this function I wrote, model contrasts, it will produce these plots. So that high temperature versus volume, adjusted for the other variables, adjusted for cloud cover. And then this is volume versus cloud cover adjusted for high temp. And there's the slope here, 5.4, and a confidence interval for the slope at the mean value of 68.8, so somewhere right around here. And anyway, I've designed these functions to be extremely powerful. It's very simple in this very simple multiple regression example, but as we go through the course in next semester, you will find that this function is going to give you a way to visually interpret the model, right? Think about looking here. Here's the model fit. What does it mean? Well, if you use the model contrasts plot, you can see immediately what the model fit looks like. Okay. All right, so we just want to interpret these coefficients. So what is the interpretation of these model coefficients? Let's go back over to RStudio. All right. What is the basic interpretation of a regression model coefficient? All right. Basically, it's let's see, I've got a long sentence I want to type, so it's basically the expected increase in y for each unit increase in x, holding all other variables constant. Okay, that is the basic idea. Okay, so that's what the beta is, the expected increase in y. Okay, so as long as we have that basic idea, that is going to be the interpretation. Let's run each of these so that we've got the plots over here. Okay. So I will just copy and paste some text that I previously wrote, which is more verbose than you need. Okay, but it basically says the coefficient for high temp is estimated at, and I've got beta hat of high temperature equals, you know what, I'm going to put the $sign at the end, equals a particular value from the coefficients table. So let's take a look. this is the second row. Second row, first column of the coefficients table. Oh, I see. All right, should be about 5.4. The coefficients table is that. So the high temperature estimate of 5.4 is right. Okay, so that's the coefficient. Thus, now we're getting into our interpretation that we wrote before. Thus, we expect volume, that's the y variable, to increase by that same amount, 5.4, for each unit increase in high temp, that's for each unit increase in the x variable, holding all the other variables constant, holding cloud cover constant. Okay, let me put this dollar sign at the end. I think that will make it look a little nicer. We'll render this and then we'll read it off of the rendered document. All right, we'll refresh this. All right, so the coefficient for high temperature is 5.4. Thus, we expect volume to increase by 5.4 for each unit increase. So what are the units, right? When we expect volume to increase by 5, that's 5 people, right, walking on the trail. For each unit increase in temperature, that's a degree Fahrenheit, okay, holding cloud cover constant. Now, here's a quick comment. Can we increase high temperature while holding cloud cover constant? Okay, so if we go back to this, notice that high temperature and cloud cover are unrelated to each other. So for sure, we can increase high temperature and it won't have any effect on cloud cover. There's no relationship here. But this is why having correlated x variables is problematic. There's multiple reasons, but one of the reasons is for the interpretation. If these are highly correlated, then it may be hard to increase temperature without also increasing cloud cover, right, if they're highly correlated. So that they are effectively independent from each other allows us to have this interpretation. Okay, and then you've got the same situation for cloud cover. All right, so as you have more, it's negative, so as you have more clouds, you have fewer people walking or biking. All right. Sorry, that's here. Sorry, I was looking at the wrong place. That's the t statistic. Yes, so for every unit of additional cloud cover, 12 or about 13 people fewer on the trail is what you expect for the same temperature. All right. So we're getting near the end now. Interpret the multiple r squared value. So let's go find that. We've got that in the summary of LM fit down here. So we've got to be able to access it. So let's go over and first access the value. Well, first of all, the value is 0.442. Okay, so we're going to remember that. Recall we've got the summary. Okay, and we can look at the names in here. We've got one that's r squared. We also have adjusted r squared. Adjusted r squared is not to be interpreted. It's only for model comparison. If we were fitting different models here with different x variables, we wanted to answer the question which of these models, fits the data best, adjusting for how many variables you have in the model, then adjusted r squared is one way to choose a model. But you never interpret it. Always use just the r squared value. So here is the r squared value. So we'll be able to print that out and then interpret it. So interpret it. So r squared, $r, r squared equals, and we're going to fill in here this value, and let's make sure signif 3 is fine, and we'll highlight what we just wrote and paste it down here and make sure that it gives us the number that we want. Okay, r squared equals that is the proportion of variance explained in volume over and above the grand mean of volume. Okay, so the grand mean already explains quite a bit of variability of volume. That is, it's finding the mean, and the variance is the amount of deviations from the mean. If you have this relationship with high temperature and cloud cover, how much additional variance can you explain? And it turns out we explained about 42% or 44% of the total variability in the amount of people. That's pretty high, I would say, for something like this. Now, if we looked at more of the variables in the data set, we might be able to explain even more variability. But that's the basic idea for that. Let's render this and see that this is going to work. Some of the highlighting in the text doesn't look quite right because we have a $ in the expression. So it's highlighting it as though from $1 to the next is the equation, and what comes after there is not the equation. But we'll see when it renders. If I refresh the page and scroll down, we have r squared and that number. And you can see the font's a little bit different from the normal text versus the equation. So anyway, all that has worked. Let's summarize our findings. Okay. All right. What do we want to say here? We've got, basically, does the model fit the data? How much variance does it explain? Was it useful to do? Okay. So I would say the regression model explains about r squared. So I'm going to copy that. About r squared of the variance of volume. And the model reasonably fits the data. That's about the model assumptions that we assessed. Therefore, I would just say here that the model will be useful for explaining, that's inference, and predicting, that's prediction, use of if I scroll up to the top, of the Northampton Rail Trail System. Period. Okay, I think that's a fine summary. All right, as a bonus, you know what, let's render this first, and then I'll show you the bonus. So the RGL, the R graphics library, allows you to do cool things in like three dimensions and stuff like that. In the car package, there's a function called scatter 3D, and a window opened and then it disappeared. Oh, here it is. All right. So this is the type of three-dimensional plot that I really like, because it's interactive and it actually helps you understand what's happening. So on the y-axis, right here, we have volume. So you know, you can rotate this in any orientation, but if you're going to think about it as a regression model, let volume go from a low value of 100 to a high value of 700 along the vertical axis. So our mind is oriented with the geometry. We have cloud cover going from 0 to 10 in the cyan axis. On the magenta axis, we have high temperature going from 40 up to 100. Observations in space are these yellow spheres, and the regression surface is that plane. So we also have the ability, can I use my mouse and zoom in and out? That's cool. We have the residual plotted. So these cyan values are positive residuals. They're the observation minus the predicted value. And the magenta vertical lines are negative residuals. Okay, so one thing to look at here is, like look around and see if there's any unusual structure. Like if there was, like say, downward curvature or something, that would indicate that there's some lack of fit happening around our regression surface. So far, I don't really see anything that's problematic with this regression fit. We do see sort of the pattern of the residuals, or at least I do, where there's tons of values close to zero, so close to the regression surface, and there's there's handfuls that are way down low and handfuls that are way up high, and that's the kurtosis that we saw, the high kurtosis in the residual histogram. So anyway, this is one way of looking at the regression surface. Let me show you a second example because we've only looked at this additive model. There's something called a model with interaction, where you multiply these values together. In a formula in R, multiplication is done with a colon. And what that allows is it should allow some twisting. Let's see if we have a twisted regression surface. Oh, boo. I tried to do too much for my computer, I guess. Let's see, get working directory. Let's see if we're in the same place. No. Let's go to session, set working directory to source file location. Okay, that's right. Now we can run everything from the top. Then we're going to run that, and this, and then I'm going to be careful about resizing this window. Okay. In Windows, if you touch the bottom of the screen, it tries to maximize. Okay, so what the multiplication usually does is it allows you to have a twisting surface, and we're not seeing any of that twisting here. Let me show you one more option. If we square this, oh no, if you square it, you just get the basically that main effect, that interaction effect. But oh, I know what I want. I want high temperature. Oops. And I want to square that. So there's this special function called I, which allows you to do calculations within a function. We won't typically use this, but let's just see this. This should allow us to get some curvature here. I think I took away an L. There we go. Wah, wah. Plus high temp. Maybe this doesn't work in this function. Or maybe I've done something, I've made a mistake and I don't see the mistake. Incorrect formula. Yeah, okay, so maybe we don't have the ability to make curved relationships in the scatter3D function. Oh well, I wanted to show you different shapes of the regression surface. So, okay, well, sorry I wasted a few minutes of your time. All right, we're about at an hour, and we're definitely at the end of the document. I hope this helped with your assignment, and I hope that you learned some things too. All right, all I'm doing is rendering it one more time, refreshing here to get that last set of answers. Okay, that looks pretty good. All right, see you next one.